How does displacement current complete Maxwell's equations? Imagine trying to explain how electric and magnetic fields work together, but hitting a snag when no charges seem to flow. That's where displacement current comes in. It was introduced by James Clerk Maxwell to fix a problem in the original form of Ampere's law. You see, in circuits with changing electric fields, especially in places like capacitors, the traditional idea of current as charge flowing through a wire doesn't quite fit. Charges don't actually jump across the gap between capacitor plates, but the electric field between them is changing all the time. This changing electric field creates what Maxwell called displacement current. It's not a flow of charges like conduction current, but it acts like a current in the equations. It's related to how the electric displacement field, which depends on the electric field and the permittivity of the medium, changes over time. Mathematically, displacement current is expressed as the partial derivative of the electric displacement field with respect to time. By adding this term to Ampere's law, Maxwell modified it to say that the curl of the magnetic field equals the conduction current plus the displacement current. This change makes the law work everywhere, even where no charges are moving, like in the space between capacitor plates. It keeps the principle of charge conservation intact and makes the equations consistent. In practical electrical engineering, this is a big deal. It allows us to understand how electromagnetic waves travel through space, even when no physical charges are moving. For example, in radio antennas or wireless signals, the changing electric and magnetic fields are sustained by displacement currents. Without including displacement current, we'd miss how these waves propagate and how devices like capacitors behave at high frequencies. Displacement current also explains how electromagnetic waves can exist in free space, where there are no charges or conduction currents. It's the reason why changing electric fields generate magnetic fields and vice versa, creating a self-sustaining wave. This concept is fundamental to designing circuits that work with high-frequency signals and understanding how antennas transmit and receive signals. So, in simple terms, displacement current completes Maxwell's equations by filling in the gaps where changing electric fields exist without actual charge movement. It ensures the equations describe all electromagnetic phenomena accurately, whether in wires, capacitors, or the vast emptiness of space. This addition is what makes the unified theory of electromagnetism so powerful and applicable across all areas of electrical engineering.